So in this video, I'm going to give an overview of optoelectronics and photonics. And this is going to be the subject of many future videos on this discipline. But what are the questions that we're trying to ask when we talk about optoelectronics and photonics? Well, the core questions are, first, how does light interact with matter? And so from our everyday experience, we sort of know that if you send a beam of light at some material, we know that some of it is going to get absorbed. So some of it's going to get absorbed. Some might get reflected back to our eyes, so we can actually see it. And depending on the material, some might get transmitted through it. So materials can be transparent, for example. And so we're interested in what's happening exactly inside this black box. So what does the process of absorption, reflection, and transmission look like? And absorption is going to be our primary focus, because this is sort of the core of how optoelectronic devices operate. And once we understand this, we're going to answer the question that engineers are generally more interested in, which is, how can we create devices? How can we create devices, with devices is spelled with an E, that manipulate light? So these are the likes of lasers, LEDs, absorption modulators, all sorts of other cool, fun devices. And once we understand how light interacts with matter, then we'll be able to start to understand and answer the question of how we would go about designing a laser or an LED, or how we go about analyzing them, like what their limitations are, what their spectrum looks like, what their emission or absorption spectrum looks like, and how we expect them to behave in a circuit. Now, personally, I think optoelectronics is probably the coolest of all the disciplines I've been a part of. And that's just because it's so complicated. Like it requires so many different domains of knowledge. You need to understand quantum mechanics. You need to understand electromagnetics. You need to understand, to a certain degree, circuits, device physics. Physics doesn't start with an S. Device physics. To a certain extent, you need to understand optics and more general electronics. And you need to understand, most challenging is how all of these sort of behave together, how one flows into another, and how they interact with each other. And so I think optoelectronics is super cool to study for this reason. And it sort of brings together many different domains of knowledge into a coherent model, which is really, really cool. And so where do we start? How do we go about figuring out how we're going to create devices? Well, we're going to start with the two energy level system. So these are just two different energy levels. These aren't bands. This isn't a band diagram like you might expect. And each of these energy levels has some wave function associated with it. So it's got some state, some electronic state that's associated with it. And maybe we've got an electron up here residing in this state. Maybe we've got an electron down here residing in this state. And we want to know what happens, or maybe we've got an electron in both, or neither. We want to know what happens when I send in light. So when I send in light of a certain frequency, or equivalently a certain energy. So what happens to this system? What happens to these electrons? Where do they go? What happens to the energies of the system, if anything? And once we understand just how two individual energy levels interact, just two, so 1, 2, from there we'll be able to figure out how entire materials interact. So from there we go to analyzing the band structure, or what's called the band structure of materials. And you might see diagrams that look something like this. So this is what band diagrams often look like in photonics. And we'll go through, don't worry if this scares you. This is an energy momentum diagram. And we'll go over what exactly everything means here, but briefly, energy is on the y-axis, momentum is on the x-axis, and this lets us figure out how electrons and holes, and in particular photons, are emitted and absorbed by this material. So a photon, for example, if we've got an electron up here and a hole down here, we're allowed to emit a photon as these two recombine with each other. So this is the conduction band, and these are the various valence bands. And so once we figure that out, once we figure out where photons are allowed to go between, and we'll also analyze things like quasi-Fermi levels, so EFC and EFV, and how these affect our absorption, or how these affect our band diagrams and how we go about representing them. Once we understand this, we can move to actually analyzing the absorption spectrum, or the absorption and gain spectrum of semiconductor devices, and specifically of bulk devices, or in other words, if I've just got a slab, for example, of germanium or gallium arsenide or something, what happens when I send in light to this material? How much of it is going to get absorbed within the material? And we'll actually be able to derive and plot what this absorption spectra will look like, or what this absorption and gain spectra will look like. And we'll figure out how exactly that depends on things like the carrier concentration inside the material. So this is alpha, and this is h bar omega, for example, on this axis. And so alpha is the absorption coefficient. And it will turn out that we can actually get negative absorption some of the time. And this is called gain. So this region where we have negative absorption is called gain. So this is alpha equals 0 on the y-axis. And we'll understand how we go about getting gain out of a material, or negative absorption. And this is the basis for pretty much all lasers. You need a material that gives you gain, and you'll see why in future videos. But it turns out that instead of just having this hunk of material here, so instead of just having this hunk of germanium or gallium arsenide or whatever light emitting or absorbing material, it's actually way, way more efficient to have what are called quantum wells inside your system. And so we'll analyze what exactly the absorption spectra looks like in that case. And it will turn out to look something like this. Instead of this smoothly varying thing, we've actually got a staircase going on. And so this is for quantum wells. We'll also briefly analyze things like quantum wires and quantum dots, and what their absorption spectra look like. And just as with the bulk case, we can also have gain in our quantum wells. So for under certain conditions, we can have negative absorption, and then it just tracks out whatever our gain looked like previously. But we'll analyze when we can get this. So when we can get this bizarre negative absorption, also known as gain, and what conditions need to be met for us to do that. We'll also go over how you actually make these quantum wells and what they look like, not just their conduction band, but also their valence band, and what the consequences are of us having two of these. And so this, for example, might be indium gallium arsenide. This might be gallium arsenide. And this is what's called a heterostructure. A heterostructure. And these are the basis for how all quantum wells are made. And this is how most modern lasers and LEDs are fabricated. So heterostructures are really the core of all of modern active optical devices. And so we'll understand how to analyze them, what their band diagrams look like, what happens when you inject electrons or holes, and where the energy levels are of this system. And from there, the last thing you need to understand before you understand lasers is mirrors. In particular, mirrors in the configuration of resonators. So we'll go over how resonators behave. So if we've got some incident electric field or some light, what happens as it bounces back and forth inside a mirror or inside a set of two mirrors. And so we'll analyze all of these bounces, and if we've got some material inside these two mirrors, which maybe it absorbs light, or maybe it has a certain negative absorption or a certain gain, what happens? So what happens here? And also, why do we even want to use resonators? Like, why can't we just stick chunks of optically active material that has a certain gain or a certain absorption and send light or send an electric field into that? Like, what's wrong with that? Why do we need these? Why do we need these resonators? And to analyze these resonators, we'll be going over the scattering matrix, which is sort of the central way of analyzing them. It's quite intuitive if you've ever taken like an RF course before, or a circuits class, or electromagnetics. And this is connected to the transfer matrix of the system. And these are actually used in practice. So I actually use these use transfer matrix simulators to calculate how my optical devices will behave in my research, and it's spectacularly accurate. Like, it's just fabulous. And after we understand mirrors and resonators, we'll finally be able to understand devices. So things like LEDs, things like lasers. Also, for example, modulators. So this is a central focus of my research right now. And so I'm probably going to make a few videos on it. But also things like photodetectors. So photodetectors, these might be photodiodes, these might be photoconductors. And we'll analyze briefly noise in all of these systems. So lasers, LEDs, and photodetectors, and how this impacts device performance. We'll also not just analyze these in what's called steady state, or how these devices behave when you just sort of apply a constant voltage or a constant current, but also what happens when you vary the current, or what are the dynamics of the system. How fast can I get my LEDs or my lasers or my photodetectors to operate? What are the limitations there? And last but not least, we need to get light in and out of these systems. And so we're going to go over waveguides. So we're going to go over how we actually transport light from point A to point B on something like a photonic integrated circuit, or just across some distance. And waveguides are the central way of doing this. So these are optical fibers, are one kind of waveguide. But we've also got slab waveguides, as well as rectangular waveguides and other sorts of waveguides. And waveguides are critical to sort of anytime you want to move light from point A to point B without a massive amount of loss between the 2 points. You really need a waveguide. Now, you could also use lenses, or you could also use an optical system, but this is the subject of optics. And so this I actually do have some videos right now in optics, and so you can give those a look if you like. And we might have time for some other special topics here and there, so I might get into coupled mode theory, which is something I've been meaning to learn for a very long time. And maybe some other advanced topics as well, depending on what the comments section pops up with. But I'm really looking forward to you taking this journey with me to learn optoelectronics and photonics. It's a really cool discipline, and I think you'll have a lot of fun. And so with that, I just want to say thanks for watching the video. And if you have any questions or comments or video requests, just put them down in the comment section below. And don't forget to like and subscribe for more optoelectronics and photonics videos.